So this page has a lot of important information, so make sure you're paying attention. So the cubic function f of x equals x cubed has 3 factors. It has the same amount of factors as its power. So since it's x cubed, it has 3 factors. In this case, all of them happen to be x. Now we can replace this x with any other factors that would happen to be, so such as x minus 2. This doesn't change the fact that the function is cubic. So what we do is we can take these factors that are the intercepts and we put them in intercept form. If we multiply all these intercepts together, it'll make intercept form. So since the graph of p of x intersects the x-axis only at its x-intercepts, the graph must move away from and then back toward the x-axis between those intercepts. So those are called turning points. Those happen between the x-intercepts. Essentially, it's where the function changes direction. So if you're going from decreasing to increasing or increasing to decreasing, those are turning points because it's where the function changes direction. Also, instead of crossing the x-axis at an x-intercept, the graph can be tangent to the x-axis. So a tangent means it touches it, but it doesn't go through it. So the graph can just touch the x-axis, but not actually intercept. The y-coordinate of each turning point is either going to be a maximum or a minimum of that function. So maximum or minimum is called global or absolute if it's never takes a value that is greater than that maximum or less than the minimum. Whereas a local maximum or local minimum, which are also called relative maximums or relative minimums, are minimums within some interval around the turning point that don't have to be the absolute or the global maximum or minimum. So max and mins are essentially the hills and the valleys that you'll see happening in your graph. Now, one other thing about the turning point, the number of turning points should be the same as the number of total max and mins. So if you've got 1 maximum and 1 minimum, you should have 2 turning points because you've got 1 maximum and 1 minimum. So we're going to graph some cubic functions here and then answer some questions. So first thing we can look at, how many distinctive factors? So how many times does our function cross the x-axis or at least touch the x-axis? I'm going to clear off the stuff I already have here. Let's erase everything and we'll plot our new functions. We got one more down here. There it is. So let's go back up here. The first one we're graphing is just the standard cubic, x cubed. So how many distinct factors does it have? How many times does it touch or cross the x-axis? Well, it only has 1. What are the graph's intercepts? Whoops, there it is. So where are we crossing the x-axis? Well, this time we're crossing at x equals 0. Is the graph tangent to the x-axis or does it cross at the intercept? So in this case, it's going to cross. How many turning points? How many turning points does it have? It has none. It doesn't have any max or mins. So it doesn't have any turning points. It doesn't change direction. It's always increasing. So again, as I just said, there's no maximums and no minimums. So the next one, we've got x squared times x minus 2. Now this is another cubic because we have x squared, that's a degree 2, and then the x minus 2 is a degree 1. So when we multiply, we add those degrees, we've got a cubic. So now let's change our window a little bit, see if we can zoom ourselves in, get a little clearer picture. Just gonna change my window size here. There, we can see a little bit better. So this time, how many distinct factors does it have? How many times does it touch or cross the x-axis? It's going to touch or cross twice. Well, what are those times? Well, it looks like that x is 0 and that x is 2, which we should actually be able to tell just from the function. So if we set this function equal to 0, because that's where we're crossing the x-axis, we can set each of the terms equal to 0 to find what those intercepts are. So that's why our intercepts are at 0 and at 2. Now, do we just touch it or do we cross it? Well, at 0, it just touches it, so it's tangent there, but it does cross at 2. So it's going to be tangent at 0, but cross at 2. So how many turning points does it have? Well, where does it change direction? We start increasing, we hit a hill, and then it changes. So that's 1. So now we're decreasing, we hit a valley, so that changes direction again, so that's at 2. And a good way to check is to count the global max and mins. So do we have any maximum values? So those are the hills. We've got a hill here at 0, and it's not the biggest number that our function ever hits, so that means it's a local max. So we're going to have one local maximum. How many minimums do we have? That's where we're looking for the valleys. We've got a valley somewhere here between 1 and 2. It's a low point. It's not the absolute lowest point, so that means it's going to be a local. So we have one local max and one local minimum, which makes sense that we should have 2 turning points. It's a good way to check. And the last one we're going to graph here. We've got x. We've got x minus 2. Oops, might help if I include my minus sign. X minus 2, and then x plus 2. When we graph it, we got 1, 2, 3 factors. We're crossing or touching our x-axis at 3 different points. Where are we crossing? It looks like at -2, 0, and at +2. Again, we should be able to see that from these factors here. If we set each of these factors equal to 0, it's going to tell us what our intercepts are. Are we tangent or do we cross? Well, it looks like at all 3 points we are crossing. So we're crossing at all 3 of those points. Turning points, where are we changing direction? So we start increasing, we hit a hill, we change directions. That's 1. We're decreasing, we hit a valley, we're changing direction here, so that means we should have 2. Change direction twice. Max and mins. So we've got one maximum, that's the top of our hill. It's not the biggest number our function ever hits, so that means it's got to be local. We have one local max. And minimums, we've got one valley here. It's not the lowest amount that our function ever hits, so that means it's going to be local as well. So this is how we can analyze different aspects of cubic functions.